In this video, I will show how to simulate the torque in a permanent magnet synchronous motor. I will consider magnetostatics with rotation. So far, I have uploaded a step file consisting 1/8 of a motor. When modeling a symmetry cell of a motor, we need to take care of three things before going any further. Due to technicalities regarding the model implementation, we need to have the rotor and stator aligned on x-axis. The rotation needs to happen around z-axis. The second, we need to have two thin domains on the periodic boundaries. The third thing, we need to duplicate the mesh later on rotor-stator interface. For that, at the moment we can translate the rotating parts apart from the stator. I will add translate and pick the rotating parts. I will translate them along z-axis. Now we can see that the rotating parts are separate from the stator. Let's confirm the model changes. Now we can go to properties. Since we consider only magnetostatics here, we can exclude the winding from the modeling domain. Therefore, all the materials we need in this simulation are the air and steel. I will add next new material for steel. Call it steel. And pick the steel parts. The only property for steel we need is magnetic permeability. In this simulation, we consider only linear materials and steel having permeability of 2000 times the permeability of free space. Let's apply and add air. All the rest are air. They can be considered as air. Now we have defined the materials. Next, I will add all the regions needed for the simulation and we'll go through them after adding. Okay, now I have defined all the regions needed for simulations. First, we have all the rotating parts, all the stationary parts, air gap between rotor and stator, the permanent magnet, interface between rotor and stator on rotor side, the corresponding one on the stator side. periodic boundary 1 and 2. The last region I added is so-called cohomology subdomain. In this simulation, the currents for the windings are applied using so-called thick cuts. The cuts are generated on the stator side, but due to technical reasons, the cut is not allowed to touch the periodic boundary nor go across the interface between rotor and stator. To avoid this, we can give additional subdomain for the function generating the cuts. Next, I will add 3 more parameters regarding the currents. I stands for amplitude of current. (300 amps) in this case. Alpha stands for angle of rotation. I will put it to 0 at the moment. And phase. This can be used later for tuning the electric angle of the field created by the windings. I will put it to 0 at the moment. Next, I will apply physics. As mentioned earlier, I will only consider magnetostatics. Therefore, all I need is magnetic scalar potential. I will introduce it to the whole domain except the windings. The permanent magnet can be modeled by introducing a background field to the magnet domain. I want the field to be 0.5 Tesla pointing outwards radially. Here the minus sign gives us the outward direction, and multiplying the field by the coordinate divided by the norm of the coordinate, we will get radial excitation. Here we need to introduce field H. Therefore we need to divide by mu0. Next, I will apply current sources for each winding. The current source can be applied by introducing a closed loop around the winding and defining the total current of the winding. Next, I will do this for each winding. Okay, with this setting for the currents, we will have a synchronous mechanical motion of the rotor with the rotating field created by the windings. Now we have initialized our model. Next we can go to simulation section. Next I will go through the script. Since there are some lines that needs to be added manually to fully set the problem, I have prepared one beforehand. I will first go through the script in general, and then I will highlight the lines that needs to be added manually. Basically, the script consists of 4 parts. First, loading the mesh. Second, defining the fields. Third, defining the problem formulation and solving the problem. And fourth, post-processing and collecting the results. Next, the lines that needs to be added manually. In simulations, we use Motor for mapping fields on the rotor-stator interface. This line sets the tolerance for Motor. Next, to have a unique solution, we need to fix by Dirichlet condition the field in one point. Here we label the point. On this line we choose any point in magnet region, and in this line we set the constraint for the point to be 0. I chose the magnet region because it's not allowed the point to be on the periodic boundaries. Fourth thing we need to remember is that as a default we will generate the cuts to the whole modeling domain. But in this case we want the thick cuts to be on the stator side for applying currents, and we want to avoid the periodic boundaries and the interface between rotor and stator. Next, we shift the rotor back. Then apply rotation according to alpha. Next, we need to add 2 lines for the problem formulation. The first line adds the continuity condition for the rotor-stator interface. Here we need to remember that the first argument needs to be the stationary surface on the stator side. The second argument, the corresponding surface on the rotor side. We address the condition for the field phi. This argument is the center of rotation. The next one, the angle of rotation we have applied. This argument is the sector symmetry, in this case 1/8 of a full 360 degrees. The last argument applies anti-periodicity. The second line for the problem formulation is the periodicity condition. We set it to the periodic boundaries 1 and 2, and the arguments otherwise are the same as above. Now we have fully set the problem. The last 2 steps that needs to be added manually are the torque calculation and collecting the results. In this simulation I used 2 methods for calculating the torque. One based directly on Maxwell's stress tensor, and the second based on Archeos method. I won't go to the details, but the main difference between the two is that when using directly Maxwell's stress tensor, one integrates over a 2D surface. In this case, the interface between rotor and stator. When using Archeos method, one integrates over an air gap volume. The volume integration makes the Archeos method less sensitive for the quality of mesh. Finally, we print the results to the log and collect them as a text file. Now we have gone through all the steps to fully set the problem. The 2 more steps we need is the generating the mesh and running the simulation. In this example I used expert setting For generating the mesh, I chose a scale factor of 0.2, and this is how does the mesh look like in this case. Next, I want to run simulation over alpha using a sweep. First, I define settings for the simulation. I choose one node and 2 CPU. Then I apply a sweep over alpha. I want to run the angle of rotation from 0 to 45 degrees in steps of 21. Press apply, and now we can run the simulation. In the end, I will show how does the torque look like in this simulation. I plotted the torque as a function of angle of rotation. From the results, we can see that when the permanent magnet is against the pole, we have higher torque, and when it moves in between the poles, the torque becomes lower. Also, the two different methods to calculate the torque resulted the same. Finally, I will visualize the magnetic flux density in steel components. Now we can see the magnetic flux density. We can also see that in the sharp corners the flux density is very high, which is typical for numerical simulations. We can see the field distribution better when adjusting the color bar. I set the maximum value of the color bar to 1. Now we can clearly see the field distribution. We can also add cliffs to the plot. Now we can see how does the flux look like inside the steel components. Now I have showed all the steps for simulating a torque in a permanent magnet synchronous motor. Thank you for watching.